I'm honored and it's really fun to be here. I've had a great day of discussions and meeting old friends and making new friends. So this is my title, and I'm going to make this introduction very short. So I'm going to tell 4 different stories and weave a theme between them. So we'll start with a little bit of an older story on wall-bounded shear flow transition to turbulence. And then I'm going to talk about a problem in condensed matter physics called Anderson localization. And then I'm going to talk about a problem in molecular vibrations, enzymes in particular. And then I'm going to talk about network dynamical systems and certain fragility and lack of robustness phenomena in the network. And the common thread is going to be fragility. And the fragility comes in various shades. I'll show you an analysis of the fluids problem where the explanation is given by eigenvalue fragility of a certain operator in the problem, while the Anderson localization problem instead exhibits eigenvector fragility or eigenfunction fragility. And then I'm going to show you another more recent work, which is about the vibrational modes of big biomolecules, enzymes in particular. And there's the phenomenon of localization, which is a consequence of the fragility in this problem. But here, the localization appears to be by design as part of the function of the molecule. So all of this is going to inspire us to look at network dynamical systems, and you'll see the connection with molecular vibrations through the swing equations of power networks, which I'll explain all of that if you're not familiar with it. And I'll show how in oscillator networks, swing equations, power grids, vehicular networks perhaps, that this kind of localization phenomena actually leads to dynamical instability. So bad robustness margins for certain types of uncertainty. When, for example, your models are neglecting delays or higher order dynamics and so on. All right, so the theme is fragility. In large-scale systems, these are all going to be large-scale systems phenomena. The kind of fragility I'm speaking of here doesn't appear to happen in low-order systems. So let's talk about wall-bounded shear flow transition. We design airplanes and ships and submarines to be very streamlined to reduce form drag. So you can then travel at much higher velocities. But then you encounter the problem of skin friction drag. And skin friction drag is caused by the fact that you have a no-slip boundary condition. So this is the flow profile against a flat layer, a flat plate, say. The shear at the wall gives you the amount of skin friction. So the higher that is, the more resistance to the flow there is. There's nothing you can do about that unless you shed your skin as you fly. But the other thing is, typically this boundary layer is not laminar, it is turbulent. And a turbulent boundary layer has much higher shear typically than a laminar boundary layer. Of course, that all depends on the Reynolds number. Similar things happen in pipe flow. So if you have turbulent pipe flow, you just need more pumping power for the same flow rate. And so it's an important problem to try to reduce skin friction drag. I think about 20 to 20% of the skin friction drag on a typical airline, of the skin friction. Half of it is about form drag and half is skin friction drag. And maybe it's to simplify, half of the skin friction drag is because it's turbulent. So if you could laminarize, you would save about 25%, somewhere between 20 and 25%, which is substantial. Now, there are systems in nature that do this. It's not exactly fully understood how. Shark skin has these riblet groove-like structures aligned with the flow that appear to reduce the turbulence in the boundary layer, the kinetic turbulent energy production. People try to replicate this in the lab by systems called riblets, but the design, it's very critical. You have to get the spacing right. You have to get the shape right. You have to get the amplitude right. And it's not clear whether you should, all of these parameters should scale with how far into the boundary layer you are. So that all of that is sort of, the mechanism is not fully understood, although I'll mention some recent progress. Dolphin skin is another fascinating example, and there it is believed that the mechanism is a fluid structure interaction. Dolphin skin is somewhat elastic, and so this fluid structure interaction somehow appears to partially laminarize the boundary layer, because dolphins have been observed to swim at speeds that, given their muscle mass, they couldn't swim at that speed unless they were at least partially laminarizing the boundary layer. At least that's what I'm told. I'm not a biologist. But the problem that got me into this field is this one. This was popular about 25 years ago, which is to have an array of sensors and actuators, shear flow sensors, shear stress sensors, and then blowing and suction actuators or micro flaps. And the idea is that you can, with MEMS technology, you can make these, not really MEMS, but sort of miniaturization, you can make the length scale about the same as the flow structures that are believed to be responsible for the turbulent boundary layer, for turbulent energy production. And so maybe by interacting with them, you can somehow suppress that process. The difficulty, of course, is that the process is not well understood. So as a controls person, the first thing I did is say, well, give me the model. Where's the plant? And of course, that I don't get an answer to that. But then I realized that the problem itself is not well understood. And so the problem is not that you don't have the devices. This is a common misunderstanding. It's that first, the process, the dynamics are not well understood. How can you design a successful controller if you don't understand the dynamics? Of course, in this day and age, data-driven methods people are going towards data-driven methods to bypass understanding of the dynamics. Okay. I'm not bad-mouthing data-driven. I think they have their place. But in this particular case, I think it's more interesting to understand the dynamics. So the mathematical modeling of transition is as follows. This is an age-old framework. You look at the Navier-Stokes equations in whatever flow geometry you have. Laminar flow, you can understand it as an equilibrium point, static, let's say static equilibrium in these cases of the Navier-Stokes equations. And you say, well, if I perturb around that equilibrium, do I come back to it? So standard Lyapunov stability question, right? And so that's when you call the flow stable. So this is, of course, all a function of the Reynolds number. And so for higher Reynolds numbers, what used to be a stable equilibrium may no longer be unstable, and you have what's normally understood as a bifurcation phenomenon. And that's the task of hydrodynamic stability, is to track these bifurcations. This is a very successful theory, and you can apply it in many, many fields. These are two of the well-known references in this area. However, in this one very important technological case, which is turbulent boundary layers, pipes, airplanes, etc., it fails. So in channel flow, you see that channel flow is up here. This is plane co-wet flow, and this is pipe flow. This is a predicted number from what's called the classical linear theory, which I'll describe in a minute. But experimentally, there's a fairly big range, which is lower typically than this number. The failure is even more dramatic in plane co-wet and pipe flow, where the classical linear theory predicts that you're stable, linearly stable, I should mention, for all Reynolds numbers. But of course, you're not in experiments. So distinguish between the mathematical stability results and the phenomenon, which is transition to turbulence. These are two different things, right? And so using the certain types of stability theory to predict the phenomenology, maybe that is the disconnect between the two. So this is often referred to as bypass transition because it bypasses the classical instability mechanism. So as an anecdote, it was widely believed that this theory fails because it's linear and nonlinear effects kick in very quickly, even for very, very small disturbances. But since the 90s, it's become a much more interesting story. There's a nice book by Peter Schmidt, who used to be at University of Washington, called Non-Modal Stability Theory, that kind of describes this. Let me get rid of this here. That describes this field. It goes by the names of non-modal growth, transient growth, pseudospectrum. We do input-output analysis. They kind of produce roughly the same results. So I'll explain why this is a fragility problem, right? So I'm going to first talk about how you incorporate uncertainty in a model. And I'm going to do it by what looks like a trick, which is to neglect certain terms and think of them as uncertain dynamics. So this is the Navier-Stokes equation, not yet linearized, but expanded around laminar flow. This is a laminar flow plus fluctuations. And the terms that are quadratic in the fluctuations are shown in red. So you can think of this term here as kind of a feedback on the linearized Navier-Stokes equation, which is everything else. You could decide to not ignore this term at all, but replace it with uncertain dynamics, because if you say, I don't know exactly how this works, so I can't analyze it, you can decide to do that. And then this delta refers to an actual dynamical system, and you have some bounds on its behavior. I'll explain what these bounds are in a minute. You could also, and this is also commonly done, you could ignore this altogether, but replace it with an exogenous input, which would be, which in this case, the way I've written it, you see the D term here, these are polarized body forces acting on the fluid. So this picture here is like tickling the fluid with sort of with forcing and seeing the effect at the output on the flow fluctuations. That's why it's called an input-output analysis, right? So this is actually the approach we took, but actually today I'm going to talk about this approach instead, because that ties in with the fragility problem a little better. But they essentially produce the same results in those two cases.
The last one would be U or U tilde.
This is U tilde. Sorry, it's too small. This is the fluctuations, yeah. U bar is just the operating point, so it doesn't matter for the. Well, it does matter for the dynamics because it's involved in these differential operators. But I'm looking at the output as the fluctuations. So zero fluctuations is I'm at laminar, non-zero is away from laminar. You could make some realistic arguments for why body forces are needed, because, for example, if you have a flow over a rough surface, you may want to model that as sort of body forces, maybe random body forces, or have a similar statistical structure to the surface roughness, more strongly towards the surface, closer to the surface than in the body of flow. There are many good arguments for trying to incorporate a model like this. In flow dynamics, a similar analysis in spirit, but not exactly like this, is called the receptivity analysis. So it's not unusual. So the interesting thing about this analysis is it reveals these underlying fragilities. To tell you, to cut a long story short, if you take this point of view, it turns out that as the Reynolds number increases, you need a delta or perturbation of size smaller to drive you to instability. And that size of that delta shrinks with the Reynolds number. So the higher the Reynolds number, the more fragile the system. It takes a very little uncertain dynamics to destabilize it. While in this picture, you can show that if you do a stochastic analysis, you can show that the ratio of the variance of fluctuations to the variance of the body forces scales like the Reynolds number cubed. And so at some point, this becomes a big amplifier of even microscopic disturbances. All right, so this is the uncertain system modeling. I think I've said all of that, so let me move on. So here's the simple, but I think very powerful idea. So this is the simplest case of robustness analysis. Excuse me. Here's a system that is very simple. It just has an A matrix, and the input enters directly into the states. And then the uncertainty is wrapped around. So these are the equations of the system. That's equivalent to this system when I close the loop. So it's equivalent to the system where the generator A is uncertain. And then what you can show is the following. This is called the small gain theorem. So necessary and sufficient version is that you can say that this system is stable for all dynamical deltas whose gain, this is an L2 gain, so that's signal to signal gain, that's a way of bounding it, less than a bound B. If and only if the system is stable for this system here, is stable for all numerical matrices delta, not systems, numerical, with norm less than B. So this converts a systems analysis problem to a matrix problem. So now I just want to look at the matrix A plus delta with the allowable range of deltas and see if that gives me stable dynamics for all of these deltas. That simplifies the problem because it allows you to visualize the perturbations, as you'll see. Incidentally, this is easily related to the transfer function norm or the resolvent norm, which I'll describe in a minute. Okay, so those of you who've heard of the pseudospectrum, popularized by Trefethen and company, this is the definition. So to define the epsilon pseudospectrum of a matrix A as follows, you perturb it with a matrix delta. That matrix is complex, possibly, or you range over all complex matrices whose norm is less than epsilon. That's the maximum singular value norm. And then you define the epsilon pseudospectrum to be the union of all of these sets. So basically think of it as the thickened spectrum of A. So with epsilon 0, you get the eigenvalues of A. And then as you increase epsilon, these eigenvalues thicken to sets that are around the eigenvalues. It's also the super level set of the resolvent, which is one way to compute those level sets. And what is typically said is that for normal matrices, when A has orthogonal eigenvectors, that's what normal means, it's easy to show that the epsilon pseudospectrum is just the union of disks of radius epsilon around each eigenvalue. So nothing too surprising happens. But for non-normal matrices, you might have unpredictable pseudospectra from the eigenvalues. The pseudospectrum can bulge in areas where there are no eigenvalues nearby, or it could remain very constricted to an eigenvalue. And I'll show you the case for the linearized Navier-Stokes here. I'll come back to
is this
yes.
an actual system that is pseudospectrum, or is it like a made up?
I made up a matrix, and the way I do it is I make the matrix so that its eigenvectors are nearly aligned, and then you get these funny shapes. Yeah. So there's another thing that this analysis gives you. So you look at A plus delta and you look at the pseudospectrum, which is a set in the complex plane. And so you're stable for all delta if that pseudospectrum set is in the left half plane. Those of you, if you work with hydrodynamic stability, the instability region is the upper half plane due to a notational convention. For us, it's the left, the instability region is the right half plane. So you should rotate everything by 90 degrees. So when the pseudospectrum bulges into the right half plane, that means there is a delta in your allowable class where A plus delta gives you unstable dynamics. But it tells you more than that. If it protrudes, say, along certain, with a certain imaginary part, that actually is going to tell you when it's like a Hopf bifurcation, and these are the structures. You go and look for the eigenvectors responsible for this, and those are going to be the structures that grow in the instability. So this is important to keep in mind. All right. So that you get that from the singular vectors of j omega minus I inverse. Yeah. Okay, so here's the linearized Navier-Stokes equations. How I get this is unimportant. This is a divergence-free formulation. The details of Navier-Stokes equations are not important. It's the fragility phenomena that I want to explain. So again, you ask about stability. Do you have any eigenvalues for this operator that are in the right half plane? And of course, you want to do this as the Reynolds number changes. Now, this is a fairly complicated three-dimensional PDE operator, but for the geometries that are important, like this, because the nominal flow is parallel, It's constant in streamwise, and it's constant in the spanwise direction. The dynamics are, by the way, this is a famous or Sommerfeld problem. The dynamics are translation invariant in those dimensions. So you can take a Fourier transform, parameterize with these two wave numbers, which here are listed as kx and kz, and then the rest is but now becomes a PDE operator in a normal direction. And then you can discretize that by your favorite methods and compute the eigenvalues. But the eigenvalues are the eigenvalues, this one-dimensional PDE operator, now ranging over all real numbers kx and kz. Okay, that's hard to visualize. So here's an example of, so here's channel flow at Reynolds number 2000. I fixed one of the wave parameters, kx, and then I let this is the green plane is the complex plane, and I let kx be the vertical axis. And so I'm plotting the this parameterized family of eigenvalues. And if I project on the complex plane, that's all the eigenvalues as I arrange kz and fix kx. Now, of course, not all of them, because I couldn't range kz from -infinity to +infinity, but that gives you an idea. So for a fixed parameter, kx and kz, I get a discrete spectrum. But if I range over all of them, I get a continuous spectrum. And this is important because now we have to go and hunt for unstable eigenvalues. And so we have to hunt for unstable eigenvalues over all kx and kz. Okay. So again, remember the failure of the theory. So the big success, Tolmain Schlichten, that's right, is computing this number, the instability for channel flow, right? So this is channel flow at 6,000, so just after it became unstable. And this is the particular wave numbers that exhibit that where the discrete spectrum exhibits an unstable eigenvalue. And the stable eigenvalue is right here. Like it barely just crossed into the right half plane. And then a big experimental success. This was done in the 30s, and a big experimental success came 10 years later to produce this the structure corresponding to this instability. It's the so-called Tolmain-Schlichten wave. This is a smoke visualization in a wind tunnel. The flow direction is to the right. This is such a weak instability. It doesn't want to show up, that in order to get it to show up, a vibrating ribbon technique was used to excite the flow upstream at just the right frequency so you can actually see it. But this was thought to be the origin of transition, and everything else happens after that. But as you see here, experimentally, the phenomenon of transition happens at much earlier wave numbers. Of course, it's highly dependent on experimental conditions as well. So something is not being taken into account in the theory. This is what I said. So except under very quiescent conditions, you don't see the TS waves. Instead, you see structures like this. You see streaky structures. This is visualization from above. And you see turbulent spot if you have impulsive disturbances. And the main sort of coherent structures you see in the flow are these counter-rotating streamwise vortices and streaks. These are depicted here. If you take this flow, let's say you take the full 3D flow, and you do a power spectral density analysis, you will see that the mode corresponding to this have very high value. Right? So you can also study it without correct. So the flow looks statistical, right? But this is the most prominent coherence. If you do POD and you look at the modes, this is the most important one. Okay, so let's look at the pseudospectra rather than the spectra. But now I have to include all possible kx and kz, all right? But because of the other analysis we did, I know the kx and kz that is responsible. So here's the TS wave. This is a 2000. So it hasn't gone unstable yet, but it's inching close to the imaginary axis, all right? And this is the rest of that. So this is the epsilon pseudospectra for various levels of epsilon, right? So as I'm thickening the spectrum, you see the TS wave is not sensitive at all to the change in epsilon. It doesn't want to move, right? Now, somewhere else this is a spanwise wave number, and this is at roughly kx equals 0, but kx 0.1 also has it. The pseudospectrum bulges into the right half plane. Okay, so if your dynamics are, there is a delta where at this kx and kz, you are going to go unstable. Okay. And then if you go and you look at the structures, this is one part, but that's on its own, this wouldn't be so exciting. But if you go look at the structures corresponding to this, the singular values corresponding to the frequency response there, okay, this is what I just said. Go look for those. The input-output resonances is one way to think about them. They look like this. So these are isosurfaces of streamwise velocity. And notice the scale here, it's much longer in the streamwise direction than in the spanwise direction. So what you see here is the structure of interleaved high-speed, low-speed fluctuations. These are the fluctuations, not the actual velocity. So that'll give you the high-speed, low-speed streaks. And these are isosurfaces of streamwise vorticity. So that gives you the counter-rotating vortices and the high-speed, low-speed streaks interleaved between them. Okay, that's in the linear model. It's just not in the eigenvalues or the eigenvectors. It is in the resolvent or in the frequency response, right? And those resemble even the structures you see in fully developed turbulence, near wall structures. So they're not TS waves, clearly, all right? This is important for control design because if you design a controller, whatever kind of actuation mechanism you have, in order to delay transition, and if you go after TS waves and stabilize them, you're going after the wrong dynamics. So that's why it's important for control design. So a lot of people try to stabilize TS waves, and they can, in DNS and so on, and maybe in experiments, but you have to have very quiescent experiments. But if you have bypass transition, it happens earlier, and your controller that's going after TS waves is not going to be doing anything useful for bypass transition. All right, so there's been a lot more progress. This is what I told you is roughly about 20 years old. And so Denise Game at Johns Hopkins has done a more refined uncertainty analysis. For those of you in controls, this is roughly mu analysis. And she gets much more quantitative agreement. So I forgot to mention, this gives you qualitative agreement, but the spacing between the structures, which is well known experimentally and from DNS, is off by a factor of 2, that wave number. And then what these people have done is that with this refinement, they actually now can get quantitative agreement as well. Mihailo Ivanovic at USC, he did what he calls a weakly nonlinear. It's a perturbative expansion, and you add in 2 terms, and you get quantitative agreements. And Armin Zare at UT Dallas has recently looked at the riblets, revisited the riblets problem with this approach, and has, I think, what seems to be a very, very convincing arguments for how riblets work. So this is the story of eigenvalue fragility. So, this has led to a lot of misunderstanding, and because when the object you're trying to study is fragile, maybe this is not the right object to study. That wouldn't correspond to the physical phenomenon. So now I'm going to talk about this other problem, which exhibits eigenvector fragility. So this is a problem in condensed matter physics, but I'm going to give you a purely math interpretation. So consider a matrix, very simple Laplacian matrix representing the finite difference discretization of the second derivative operator, and add diagonal randomness to it, IID random variables, and with a small variance, let's say epsilon variance, right? And we consider large matrices. So the question is, I know the eigenvectors of this matrix. So here's what they look like. Of course, this is a very large matrix. So here, if you see, this is 100,000, very big matrix. And the eigenvectors basically look like sinusoids. So I plot them now because I don't want to write down an eigenvector with 100,000 components. And now I add a tiny bit of randomness, and the eigenvectors look like this. So here is a absolute value plot, and here's a semi-log plot. So you get this is the first 5 eigenvectors. They are peaked at random locations, and then they decay exponentially from the peak, as you can see in the semi-log plot. Okay? And basically, as n goes to infinity, any epsilon of variance of the diagonal perturbation will cause the flip from this nature of the eigenvalues to this nature of the eigenvalues. So for infinite matrices, almost surely all eigenvectors are localized for any arbitrarily small amount of randomness. So highly fragile. But of course, you need high dimensions to see that fragility.
So
Yes.
the green is what is that 0? Or is net not negative, positive?
Here,
Mhm.
that's 0.
Okay, that's
Yeah, that's 0. Some of them are negative, some are positive. Yeah. Here's an absolute log of the absolute value of VK. Sorry. Yes. Good eye. Yeah.
I'm getting old.
So what about the eigenvalues? Right? The eigenvalues are not fragile. This is the unperturbed spectrum, and this is the perturbed spectrum. Well, they just expand a little bit, right? So the eigenvalues are fine, right? After all, this is a symmetric matrix, so its eigenvalues cannot behave very badly, but the eigenvectors can. All right, so this was done by, so this what Anderson in 58 showed is that the example I gave you is about a 1D Laplacian, and he showed that in dimension 3 and higher, you need a non-zero variance, which is called the disorder, in order to have this change in the nature of the eigenvectors. And this is important in basically in models of crystal lattices, where you think of this as the Schrodinger equation for an electron in a crystal lattice. This corresponds to the Hamiltonian of, say, this happens with periodic Hamiltonians as well, of the crystal lattice, and this is a small amount of disorder. So the result is that if your crystal is 1D, your eigenfunctions are always pinned. And that means the electron cannot move. While when the eigenvectors are delocalized, the electron is free to move. It's a transmissive medium. And so in 3D and higher, and depending on the crystal lattice structure, you want to find the threshold for when your eigenfunctions flip their nature, and this is called the metal insulator transition. But it is about the fragility of the eigenvectors to medium disorder. Right? So I'm going to show you, before I get to networks, one last intriguing example. So by the way, Anderson localization is still a very active area of research. There's a lot of interest in both physicists and applied mathematicians. And now recently, there's this group called Simon's Collaboration on Localization of Waves that have been finding these localization phenomena in many other physical systems. And I'm going to tell you about one of them, which is about the effects of geometry, not randomness. Okay, so that's so I'm going to talk about vibrational modes of large molecules. So a classical model for the vibrations of molecules is just to model the atoms as masses connected by springs, which are the bonds. Okay, let me get back to this. So what you do is this is the simplest linearized model, say, of the vibrations. These are the masses, these are the spring forces. So what you do is you can move into what's called normalized mass-weighted coordinates, and then you end up with a vector second-order systems, the kind you study in vibrations analysis, where now you can call L the Laplacian matrix of an elastic network. Okay, so the eigenvalues of L, square root of them, they give you the vibration frequencies, and the eigenvectors give you the vibration shapes. Right? And let me now tell you what they applied. They applied this to enzymes. So enzymes are large biomolecules, which are responsible for catalysis of many biological processes. In fact, they can speed up reactions by about 4 to 5 orders of magnitude. Some people say without them, life would not exist because they're very important for all biological reactions. They work by changing the conformation of molecules. So what they have is 2 sites. There's something called a binding site. So another molecule comes and binds to that site because of its 3D shape, lock and key mechanism. And then there is another site here, which is called the catalytic site. And that interaction with that site causes the attached molecule to change its conformation. And when its conformation is changed, it can follow a different reaction path. That's the catalysis. Okay, so what this group did, it's a group in France, is they took 3D models of many enzyme molecules. This is available with X-ray crystallography. You can get the exact shape. You have models of the strength of the bonds between atoms. And what you do is you can write down the corresponding elastic network Laplacian. Now, this is a matrix. This is a sparsity pattern of that matrix. The enzyme starts out as a chain, one-dimensional chain, as it's read off by transcription. And so you can label the molecules by their index on the chain, and that's the labeling used to form this matrix. Now, of course, it folds, and so things that are far apart in index can be close in 3D. So keep that in mind. So then they analyze the eigenvectors and eigenvalues of this. So at the highest frequencies, which are in a range of 3 terahertz for this molecule, they discovered that the eigenvectors have a lot of peaks, very isolated peaks, right? The lower frequencies don't have that. They're much more sort of supported everywhere, right? So this is here, I'm showing the top 10. And now if you look at where those sites are in 3D, this is the picture, right? So they're all located in one place, roughly. And remarkably, this is what's been known to be the rate promoting site. That is the catalytic site. So apparently what happens is this other molecule docks, and then at this very high frequency, this site has a very high displacement. And that seems to be what maybe that's what triggers that other molecule to change its conformal shape, right? And so they did this for many, many enzymes, and it's consistent across all the enzymes that they looked at. The eigenvector localization regions correspond to what's been known by biochemistry to be the rate promoting site. Okay, so that's remarkable. Here, there's no uncertainty, there's no disorder. Probably, I don't know if they're unmodeled dynamics. I mean, these are microscopic systems, right? So this is kind of by design. This is not a result of a fragility. So how come systems that have complex geometry but no disorder exhibit localized eigenvectors similar to those that have disorder? One possible explanation might be this, and I'm going to do it for PDEs. Imagine you have the Laplacian of wave propagation with constant coefficients in a domain that has a very irregular boundary. That's the complex geometry. You can always, provided the boundary is, say, not too bad, you can find a transformation to transform this boundary into a sphere. And that's a domain transformation that's changing your domain omega. So this has very simple geometry. But if you now look at the Laplacian operator in these new coordinates, the transformation, well, I'm calling it A here. The transformation is T, but this A of Y here becomes if you think about it as the wave speed, that's a complicated function of Y, and it's complicated because this transformation is complicated. So here you have a wave equation, or the propagator of the wave equation, over a simple geometry domain. but with highly irregular wave speed or coefficients, or obstacles, if you will. While here, it's the shape of the boundary that is where the complexity is. So in a way, the molecule is kind of the discrete equivalent of that. It's the complexity of the shape that gives you the localization of the eigenvectors. Okay, so what does this have to do with networks? All right, so this is work with my student Purva Shukla, who's graduating this summer and looking for a postdoc. Is anyone interested? So this is about distributed network control, but I'm going to use the example of phase synchronization in AC power networks. So if you don't know this, it's very simple. These are rotating machines, generators. They all rotate in synchrony, same frequency, hopefully, and very closely locked phase, depending on how much power is being transmitted. But let's say zero phase distortion is what you want. But when their phase fluctuates, ooh, I lost that picture. Okay, sorry. When the phases fluctuate, this is the picture I don't have. They send the reactive power back and forth. This is how they signal each other, and they tug on each other so as to basically to follow the same phase, right? All the Western United States is a single grid synchronized frequency. A generator down in California is talking to a generator up here constantly. Yeah. So this is the model. This is the simplest. So this is a little bit more. This is a second order Kuromoto model, but we're going to look at the linearization because we want to look at under good conditions when everybody is synchronized. This is the model that matters. What happens with small fluctuations, right? So this is it's a Laplacian. It comes from the imaginary part of the network admittance matrix, but for us, it's a second order oscillator network, right? By the way, incidentally, so when you have disturbances, this is a system that is capable of wave-like phenomena. Electrical effects travel at roughly the speed of light, but this is an electromechanical system. Generators are also involved. So the dynamics are not just electrical. So the waves that propagate are called electromechanical waves. And they roughly have speeds of about 100 to 1,000 kilometers per second. Much less than the speed of light. So we asked the question, are there networks with localized eigenvectors? And what does that mean for stability of the networks or fragilities to unmodeled dynamics? So turns out there are a lot of networks with localized eigenvectors. This is the simplest example. It's really laughably simple. This is the graph, but this is what the sparsity pattern of the Laplacian looks like. And this is a plot of the eigenvectors, all of them. This is 200 in this case. This is the eigenvalue index, and this is the node index. So I'm plotting the eigenvectors over the nodes as indexed linearly. But this is not a one-dimensional network, so be careful. It's just the way I decided to index it. But what you see is the following. This is the spectrum. These are the eigenvalues. The ones labeled in red all look like this. They are localized. They're peaked, very peaked, and then zero almost everywhere. And the ones labeled in blue are kind of spread out over a region that is complementary to the region where these have their peaks. And there are a few that are kind of spread out everywhere. Here's another example. In this example, the localized eigenvectors happen to be towards the lower eigenvalues. In this example, they turned out to be towards the higher eigenvalues. And here you have localized and then spread out and trapped eigenvalues. So that's another. What you see is that, and we kind of have an understanding of this, but we're still working on it. But in all of the examples, the network seems to split into two regions, complementary regions, roughly, where the red one here, so this is a plot of all the eigenvectors on top of each other for a network of size 6,000. You can call this region of the graph localized, and we call this region of the graph, the blue, delocalized, right? And so what I want to study is the fragility if I perturb the dynamics in one region versus another. So here's what I'm going to do. I'm going to perturb it in two different ways. I'm going to put disturbances, so like an impulsive disturbance entering at the kth generator and then propagating through the entire system. That's like an impulse response. Or I can have unmodeled dynamics. So I'm going to have a little bit of damping, and so here I'm adding damping, but I'm going to perturb. I'm going to show you how I'm going to perturb in a very structured manner. So let's see the impulse response case first. So here I put an impulse in the localized region, and then you see that the response is confined for a long time. These are longer time scales here, to 10, to 20, to 200. But over long times, the waves seem to propagate, but not with large amplitudes, but they concentrate at this other point. That's because this eigenvector, the eigenvector which has its support near the node that I perturbed, has two peaks. And so what happens here is that very weak waves travel, and they have a constructive interference pattern at the other end, where that other peak is, and they concentrate here. And then the reverse process happens, and they go back and concentrate here. So these two nodes are talking to each other, but through messages that are barely detectable throughout the network. If you disturb in the delocalized region, you get much more of a spread. All right, but now the robustness picture is more interesting. So a second order oscillator network for the AC transmission system is a laughably simple model, right? A generator is not a second order oscillator, right? A generator is a giant machine with lots of unmodeled dynamics. A transmission line doesn't instantly transmit without delays, et cetera, et cetera. So it's very natural to have these perturbation models, which are dynamical systems. And notice this, how they enter here. They enter in a very structured way. So this is the link between node K and node L with a little bit of unmodeled dynamics on it. And that is modeled this way. It's a rank 2 perturbation of this matrix L. Right? I can do the same thing for node, which have a self-answer. So this, if your generator is not behaving like a second order oscillator, you may want to do that. And then here is a rank 1 perturbation, right, of the matrix. So again, let's recall this type of analysis. Instead of A plus delta, now I have this structure. So A plus B delta C, because of the low rank structure of the perturbation. And I'm going to look at the pseudospectrum for that. Remember what was said, that it's only interesting for non-normal matrices. But that's only if you perturb with A plus delta. If you do a more structured perturbation, which I'm doing here, because this L is a Laplacian. It's certainly symmetric, right? So it's definitely normal. But I'm perturbing it in a different way than the way people usually do with the pseudospectrum. So you will see that we will have surprising behavior even when A is normal, if you do a structured perturbation. So this is, we'll call this the compressed or structured epsilon pseudospectrum, and we compute it in a way that all of you who know controls will find to be the level sets of a transfer function. Okay? So here's the compressed resolvent norm pseudocolor plots. So this is just for the Laplacian, not second order network model. And so the eigenvalues are real and positive for the Laplacian. And here's the when I perturb it, this is the plot of the pseudospectrum. Actually, I should just show you the pseudospectrum here. Let me not. So here's the second order oscillator network, and I'm looking now at the eigenvalues of this full matrix, all of this matrix, with a perturbation like this. And I'm going to compare a node perturbation in the localized region to a node perturbation in the delocalized region of the same size, same norm bound. And you see, and this pictures are to scale. You see two things. Only the localized eigenvectors that have support near that node get perturbed, but they get perturbed by a lot. Compared to here, many eigenvalues get perturbed, but by a small amount. And so this is a zoom in that shows you. So for these parameters, the system will go unstable. And so I'm running out of time, but I'm going to tell you just a couple of things very quickly. We can do a sensitivity analysis, standard sort of analytic perturbation theory of eigenvalues and eigenvectors. And the quantity that comes out to be important, this is the first order sensitivity, is given by various components of eigenvectors. So I'm going to talk about that for a little bit. So here's this quantity, which is the first order sensitivity of eigenvalues. VIK, that's the sensitivity of eigenvalue I when I perturb node K. Okay, and I'm looking at the maximum over all eigenvalues. So this is the susceptibility of node K to perturbations. And you see here that it's about an order of magnitude higher in the localized region compared to the delocalized region. Similar picture for edge perturbations, okay? Furthermore, in this example, if you grow the network in a certain way, like keeping the ratio of the band size to the network constant, that discrepancy of one order of magnitude here grows to infinity. So it grows unboundedly with the network size. So why is this happening? So here's an intuitive explanation, which maybe can be made more rigorous. Again, this quantity is the key. So it's actually known in the power systems literature as the modal participation, meaning this is a little tricky with the terminology because mode and node are very close in sound to each other. So this is how much node K participates in mode I. Mode meaning the eigenvector, right? So it's the value of the eigenvector I at node K. So what we know is that in the localized region, there are, for a given node, it participates in only very few modes because the localized eigenvectors are spread in this region. And so this node may participate in 2 or 3 modes only, and the rest is negligible. And those 3 modes, the nodes that they participate in is also a very small number. Okay? While in the delocalized region, because the eigenvectors are spread out, each node participates in a lot of modes, and each of those modes have many other modes participating in. So I feel like the nodes in the localized region are modally lonely, right? They don't have a lot of nodes to interact with through the modes, right? And so what happens in a oscillator network model for phase synchronization is that if you go out of synchrony, all the other nodes tug on you to help you stabilize, right? So the more you interact with other nodes, the more likely they are to stabilize you. If you're modally lonely and you're in trouble, you have very few friends. So we came up with this notion, what we call modal connectivity. So the modal connectivity of node K to node L is basically this kind of dot product between the absolute values of vectors. If there's overlap, then mode I, if there's a big number here, big overlap, then mode I connects K and L well. And then if you sum over all the modes, that's the total connectivity of node L to node K through the modes. And this is different from other network distance measures. Like, it's not even a distance measure. It's different from resistive distance. So we have examples where they're not the same as the resistive stiffness or graph distance, because this notion is really about robustness on model dynamics, which is not really what these other distance measures were built for. Okay? So this is the thing that with this current work, we're studying this, as well as trying to figure out what is it in the geometry of networks that causes the emergence of localized eigenvectors. So there are lots of interesting questions and remaining, and I think I tried to weave the thread. And if let's just remind you, we went from eigenvalue fragility and then to eigenvector fragility, which came because of localization. So the expression of that eigenvector fragility was localization. But then we discovered localization as a sort of by design, for function, right? Because these are systems that maybe are not susceptible to disorder for the particular type of dynamics, for vibrational dynamics. But there seems to be a connection between, in systems in which uncertainty exists, there seems to be a connection between localization in the other way around. Localization produces fragility, while in the Anderson localization case, fragility produced localization. So this interesting circle of ideas that we're still trying to think through. And I will mention again, most of the localization work is from Purva Shukla, who is looking for a postdoc. All right, thank you.
Thank you so much. Any questions for Bassam? I like the fact that you went through all the different applications, power, fluid,
Yeah.
synchron, yes.
Yes.
Out of curiosity, was that enzyme a single linear chain folded around, or did it have branches?
I don't know the answer to that. I think when it's during transcription, it's a single chain, but then it folds. So I'm not sure. What do you mean by branches?
Well, side branches. In organic chemistry, they'll talk about, I think they talk about side branching.
That's beyond my expertise. Yeah. For me, an enzyme is a network of second-order oscillators for vibrational purposes. Yeah. So I don't know the answer to your question. Yeah. I know that when they studied this, they used the results from X-ray crystallography for the three-dimensional shape. And then the chain part is simply for the labeling of each of the atoms. Yeah. Yeah. Yes, indexing. Yeah. Yeah.
First question is, are you using some standard IEEE network to model this, or were you like, because clearly each local node is a different dynamics.
Yeah. So this is not these are not real power networks. These are examples we made up. Right. So we're now studying the European power network. As you know, there's been a lot of data that came out because of the failure in Spain last year, which propagated significantly. And they're intriguing, stories about how, you look at the frequency variations. There was a bus in Spain and a bus in Latvia that had, so the bus in Spain was causing these frequency fluctuations. The one in Latvia was really fluctuating a lot, while all the ones in between were fluctuating a lot less. And so there's not, maybe this is an explanation. I don't know. So we're looking at the real data. So that database exists. So we've just started looking at that this month, actually. So you have it has a lot of it. You have the inertia of each generator, the damping, connectivity. And so it's, we're doing this now. So yeah, clearly we want to apply this to real power systems, yes.
But does any of this patient remotely feel like it fits what you expect from the theory you come up with? I really like the explanation at the end, like the model.
Yeah. So, I mean,
I guess my question about that was really, is it a phenomenon really exists in the real power systems?
I mean, uncertain dynamics are definitely there, right?
Yes.
Right. So this is a very simple model. Generators have a lot of uncertain dynamics and buses and transmission lines. So it's natural to try. Now, the thing is, do you guys teach robust control here still?
She teaches.
Okay. So I ask this question everywhere I go because not many people still teach it. But if you remember the small gain theorem, the destabilizing deltas, when you prove necessity, they're typically either delays or non-minimum phase systems, right? So those are the dynamics that destabilize you. And so it's not implausible that, in these models, you could have delays in non-minimum phase dynamics, right? Delays in particular, maybe. Yeah. Yes.
Great talk.
Thank you.
Usual, but very intriguing. The part I was, so of course, about nodal domains for the Laplacian, right?
Nodal domains.
They call it nodal domains, which is like the sign changes in the eigenvector.
Yes. Yeah.
So plus
For graph partitioning, you would use it.
So the second smallest eigenvalue, the second one would be used for, but the third one also has some.
Sure.
So like
Yes.
Like 3 sign changes, 4 sign changes.
Yes.
So there's a sign pattern to the structure of the eigenvector. And I wasn't sure if when you look at.
Good point.
There are some connections here too, right? And some of them are connected also to this notion of symmetry and automorphism.
Yes.
Of the graph.
Yeah. So we can generate, they are related to symmetry. The way we can now generate a very large number of examples from this, of networks that have localized eigenvectors. The way we do it is we take some network that has a lot of symmetry, like a circulant graph or something like that, and then perturb a part of it with a perturbation. And here's the interesting thing. So what you need to see localization, to do that, is you need the perturbation and the original symmetric network to have the perturbation is also Laplacian, so it has its own eigenvectors. You need those sets of eigenvectors to be almost mutually orthogonal. Now, this doesn't happen in low dimensions. In low dimensions, if you take two orthogonal sets, the most you can make them orthogonal is 45 degrees. But in higher dimensions, you have a lot more room. And in fact, as you grow, you can make two orthonormal systems that are almost orthogonal. Right? And I think I forgot how the sign of the angle it scales with square root of n, something like that. Right? So provided you take a highly symmetric network and you take a perturbation whose eigenvectors are almost orthogonal, and you will get this phenomenon. And one more thing. The perturbations we use all have localized eigenvectors. And the localized eigenvectors, like PT, and if you think about a symmetric like a circular network, its eigenvectors are all the sinusoids. And so they're almost orthogonal, and that overlap, the amount of overlap goes to 0 as n goes to infinity. So that's why this construction works. But in general, that's what you need. So it's an interesting question about large matrices. So, two large random matrices will have almost symmetric matrices, will have almost orthogonal sets of eigenvectors. But these are not random. So, but we have to construct them that way to construct all the examples.
And the circular net, I think you get the DFD.
Yeah, they get the sinusoids. Yeah. Which are spread, and then if you perturb with something that has peaky eigenvectors, then the dot product is negligible as n goes to infinity. Yes?
So these things won't happen for a random perturbation, right? It's for constructed perturbation that you see the difference.
Yeah, this is a very deliberate perturbation around nodes and edges. Yeah. So I don't know, there are many other kinds of perturbations you could choose, but we thought these are, where is it? Physically plausible. Yes.
Little bit randomly. Will this phenomenon still happen?
So
like taking the bad cases, but perturb them a little, or like randomize them a little.
Randomize first, or
back perturbation and add maybe a little bit of random.
I see. Yeah, yeah. Oh, you mean how robust is the fragility? I see.
Yeah, do you have to really think hard about coming up with this special?
How robust is fragility? I think
Is
the
it,
robustness analysis is robust, right? So,
is there a name for it?
I don't know.
Robustness of fragility.
So, so you're saying if I take this delta and I find a destabilizing delta, let's say I found just the right delay with the gain within my bound that destabilized the network. And then I do a random perturbation on top, slight random perturbation. I think the answer will be the same, but
Like the phenomena remains.
I think so. Yeah, I think so.
Let me ask
That's my intuition, but I have to show it. Yeah.
another version, like for the network that you showed, like the circular networks. Is there any particular way that you have to assign, like you have to assign these edges for the localization to happen, or does it happen for any network that doesn't happen?
So for example, to form this, think about this band without the squares here, and then complete it so that it's a circulant matrix. And then you add a perturbation to make this a square here and to remove this part here. So that perturbation on the circulant matrix has the properties I was just describing. And therefore, and actually what you can show is that in this case, yeah, well, I shouldn't say more because this is something we're trying to completely characterize. Yeah. But it's not a rare phenomenon. Yeah.
Any questions from audience on the Zoom? Okay. Okay, so let's
Thank you.
again. On behalf of